Today we will continue to discuss discoveries of particles. Now we know a lot of different particles, I think thousands if you look at the particle data group for publications and the tables with many particles. However, few of them are extremely important and they played key role in developments of our theory. So of course electron is extremely important. Discovery of positron is to some extent expected. But what I will discuss now is really unexpected discovery, and you will see how important conclusions and principles emerge from discoveries and studies of properties of particles.
Did you start recording?
Yeah, I think I did. So what I will discuss today is discovery of muon first. Extremely important particle, not only from conceptual point of view, but also from practical point of view, because muons is kind of the problem for many experiments. This is it's very penetrating particle which actually produces problems for experimentalists, and the fluxes are huge. So the flux of muons, for instance, at the Earth, at the surface of the Earth, is something like 10 to the 4 muons per minute per square meter per minute. So I can imagine how big is the flux. So we are kind of at the shower of these muons.
Because of Coulomb breaks? Because of Coulomb breaks? Or cosmic rays?
Yeah, so that's the origin is cosmic rays and secondary cosmic rays. Muon has been discovered by Anderson and Neddermeyer, Carl Anderson. The same has discovered positron and Neddermeyer. I think Sean S. In 1936, few years after. The source of muons was cosmic rays, secondary cosmic rays, and the detector was again Wilson chamber. So what are the observations? They saw the tracks of the particles, and again, almost the same setup as for positron. The chambers with lead plate inside. And then they saw the tracks, rather thin tracks, so observations. With rather small energy loss in the plate. And they have also magnetic field. And the charges, at least the first set of the measurements, mostly were negative, so negative charge. Negative electric charge. So this means that we deal here with kind of penetrating particle with high penetration ability in contrast to positron. So the average momentum of energy of these particles was several hundred MeVs. So I see that you are unhappy with kind of dirty thing of these discoveries, right? It's something like, some tracks or some bubbles, so not precise. But this is how things developed and how we actually constructed our beautiful theory, right? With all these nice formulas and Lagrangians. But this is how everything emerged. So they saw these tracks. Now, how to interpret this? So by that time, again, mostly people are using exclusion principle. Number of particles known was quite small. And the idea is that can be proton, but the charge is negative, or maybe antiproton, or it could be electron. So proton or positron. So the charge was, I think it was positive, because negative muons are captured. Well, they actually discovered both positive and negative. So the problem is to distinguish between proton and electron, or positron. Negative muons actually captured well by nuclei, so that's the bigger flux was from positive. So how to distinguish these things? If it is proton, then it should be non-relativistic. And so you can compute what is the ionization energy loss for the proton with this momentum. And it turns out that the energy loss is quite big. So one would expect significant energy loss when particle crosses this lead plate. And the track would be much thicker than this, what they observed. Too big energy loss. However, the energy loss would be smaller if the mass of the particle is smaller than the mass of the proton. So if you start to decrease the mass of the particle, then it moves faster. Remember, the velocity becomes bigger, and therefore the loss of the energy is smaller. Remember, in ionization formula, there is 1 over V squared. So that is excluded. Now, if electron, then it is ultra-relativistic, right? The mass of the electron is half of MeV, and here is several hundred of MeVs. Then the electron should be highly relativistic. And therefore it will lose a lot of energy on radiation. Right? So you can compute what is the energy loss. Again, the same story. One would expect, say, very strong, very big energy loss inside the plate, and one would expect the track like this after crossing. However, if you increase the mass, then the energy loss onto radiation decreases. So, which means that you can explain the observed events, the properties of the events, if you take the mass somewhere in intermediate range between the mass of the proton and the mass of the electron. And the conclusion was that you can fit the tracks, the size of the track and the change after crossing the lead if the mass of this new particle X is 1 over 10 of the mass of the proton, approximately. Anderson called this particle mesotron from meso, which means intermediate in the Greek. just because of this, because the mass which is needed is intermediate between the mass of the proton and electron. And that was discovered, if you like this or not. So this is how muon has been discovered. So the conclusion was that these tracks correspond to some new particle, charged particle, and the mass should be around 100 MeVs, so 1/10 of the mass of the proton. Okay? So the number of these events observed was quite big after some time of observations, and they also observed that this particle is decaying. This particle is decaying, and sometimes they saw the tracks of the following kind. Decay. Now we will discuss decay. So now we'll use the present day name for this particle, not mesotron, but methon or muon, and I will use this notation for this particle. So they saw later the track that you have something like this, and then something like that. So what is this? This track has been identified with the track of the muon, and this one with the track of electron, positron. So what is the interpretation? How you would interpret this? So, see, this is what experimentalist was seeing. So how you would explain this? Clearly what happens here is that there's energy momentum non-conservation at this point. Right, so how you would interpret this?
There's a third particle.
So let me put here. So that's experimental material.
You need neutrinos.
Okay. So the first idea is again, so now if there's something missing energy or momentum, everybody is blaming neutrinos. So neutrinos are emitted here. You do not see neutrino. So in different events, let me give a little bit more information. The energy of electron was different. So to say, we have a continuous spectrum. Energy spectrum of electrons. So this is important observation. Of course, the energy of, so what happens is that this particle most probably stops and then decays, and therefore one would expect that probably the energy should be the same in all the decays, but what has been observed that the energy changes from one decay to another one.
Why in that time this cannot be just a photon?
What?
Why in that time, in this context, this cannot be just a photon? Just an emission of a photon from...
Well, photon, you would see photon, by the way.
Also,
so there's something which, by the way, we will come to this question about the photon. So we are still struggling to discover decay of muon with emission of photon. That hasn't been observed till now.
Right, so, but if there is a continuous energy spectrum of E, that it means that there is a fourth particle as well.
There is what?
The muon should decay in 3 particles then, because if the energy
right. So correct. So because if you would put, you would have just 2 particles, that the energy is fixed by energy momentum conservation, and the decay is at rest. So if you have 2 particles, they will just be moving in opposite directions, and the energy is fixed.
But we can also say that because we are having a detector which is filled with gas, then the electron might scatter from the gas, and that's why the energy spectrum is, continuous.
In principle, yes, but that can be estimated, and as in the case of Anderson experiment with positron, these effects are small. So and you see how this curvature changes. Actually, you can guess what is the energy loss because of. Otherwise, if it would be a big energy loss, you would see something like this.
And we can also say that if suppose the third particle is a neutrino, then we cannot satisfy the conservation of spin angular momentum because.
So wait a minute. So step by step.
Okay.
So from this observation that the energy spectrum is continuous, we need to guess that there are 2 neutrinos emitted, not just one, but 2 neutrinos. And then you will have 3 particles in final state. And as in the case of beta decay, we can explain the continuous spectrum of electrons. Okay. So let us summarize interpretation. So it's missing energy and momentum is due to neutrino emission. Second, 2 neutrinos are needed. Continuous spectrum. Two neutrinos. And so we have now the process as mu go to electron, neutrino, and neutrino.
It should be one antineutrino electron and the other neutrino muon.
Well, so you see that was in 30s, and the idea of 2 neutrinos actually emerged later. You see how things develop. In the first place, people just thought maybe just a 1 neutrino. Now, what is important from here, since these particles have spin 1/2, then muon should have some integer spin, right? And the simplest possibility that if spin is 1/2 also, then you can satisfy angular momentum conservation. All the one needs to check that if it is 1/2 or 3/2 or maybe 5/2, that has been checked later. So some integer spin. Now let us construct the theory of muon decay. What is the theory of muon decay? And what is important that here again we use analogy. And you see all the things develop by analogy. We have muon, and we have neutrino and neutrino. So it's muon, neutrino, electron, and neutrino. It looks like beta decay. In the beta decay, we have emission of electron and neutrino, right? That looks like, as in the case of beta decay. However, here instead of a neutron and proton, we have muon and neutrino.
Why don't you put the modern notation of including the family of each neutrino and putting antineutrino, for example?
Well, one of these should be, so let's see, if this is muon, this is electron, then what is here antineutrino, and this is, and here it will be neutrino.
Neutrino muon.
Yeah, now we know that this neutrino mu, but it took, say, 30 years before we came to this conclusion.
You know, we can now predict it because we know the left function number should be conserved, but we didn't know.
We know because of experimental data, first of all, right? So because we haven't seen some transitions, otherwise it could be just 1 neutrino. And again, people always try to use the principle of economy or simplicity. So don't introduce without any, say, good reason some new particle. And we'll come to this notion of lepton number. Anyway, that looks like beta decay, and therefore we can say that probably on here we have interaction of 2 currents. One is already known, and it is formed by neutrino and electron. And then another is formed by muon and neutrino also. So then we can write Hamiltonian, again using analogy with what we know already from beta decay. So you see how we build up the theory. So step by step we're using analogy and using similarity. We can write Hamiltonian in the way we have written for beta decay. So let us put G, but now mu. square root of 2. And then a product of two currents. One is the electron current. Let me write it in the modern form, neutrino. And another current is current of with muon and with another neutrino. And if you want, I can write here muon. So if you want. So this is the first current, and then the current is gamma mu 1 minus gamma 5. And we will come to this gamma 5 later. And mu. So this is S in beta decay.
Shouldn't it be anti-muon electron neutrino?
Sorry?
Shouldn't it be anti-electron neutrino and muon neutrino should not be the anti?
So let's see if electric charge is conserved, so mu is absorbed and electron is produced. I think it's correct. So you need to check that you have electric charge conservation. But of course, if you introduce this Hamiltonian, you need to also add Hermitian conjugate, which will have the currents which kind of interchange muon and neutrino, and here electron, neutrino, and electron.
Okay, so you by the new bar you mean the outgoing neutrino. I thought that you mean that it is anti-neutrino. That's why.
Also, that's a bar. This is Dirac conjugation. Sorry. So also, like here, this is Dirac conjugation. But you can interpret this. That also contains absorption of antineutrino. So let's feel this production of neutrino and absorption of antineutrino. So you see, we have this Lorentz structure, which is similar to what we have in the beta decay. And here both currents have this, what we call V minus A structure. So this is vector current with gamma mu, and this is axial vector current. So we will discuss parity violation in a couple of lectures from here. Okay? Now, people measure the energy spectrum of electrons, and it has quite interesting form. Well, actually, this energy spectrum depends on what you put here on Lorentz structure. So the energy spectrum, number of electrons with a given energy E, it has the following form. It increases, and then there's a sharp cutoff at say mass of muon over 2, which is maximal energy which electron can took, because that would correspond to situation when you have two neutrinos emitted in one direction and electron is emitted in another one. So it takes half of the energy available, which is the mass of the muon. Okay? So again, this form depends on Lorentz structure of these currents, and that corresponds to V minus A. If it would be V plus A, then the form would be like this, with maximum somewhere in intermediate range and not close to the end point of the spectrum. So measuring this spectrum, you actually can confirm that we have parity violation and V minus A theory, which we will discuss later.
Where is B plus A?
Sorry?
Where is B plus A?
V plus A would correspond to plus sign here.
Oh, I see.
Sorry.
So one of them is a left-handed current and one of them is a right-handed current.
What is left hand?
You know, if you introduce one minus, right?
Yeah, so that will correspond to, I will introduce this later, so left hand or right. Okay? Now maybe I should say something, or maybe not. This spectrum, the form of the spectrum, you probably will meet this somewhere, these terms depends on so-called Michel parameters. So, in the first studies, people didn't know what is really Lorentz structure, and so they introduced so-called Michel parameters. So Michel has introduced these parameters, and one of the important parameters is rho, which actually gives you the spectrum, and the spectrum looks like 3 minus 3x. I will explain this one, plus 2/3 rho, and there's 4x minus 3, and so this is dn over dE. It's proportional to this. This is rho parameter, and x is energy of electron over maximal energy of electron. So it's 1 if you are sitting here. And rho is determined by Lorentz structure, by properties of these currents. And for this V minus A structure, and so what people did actually, they measured the spectrum, and in this way they measured this Michel parameter. And in the case of V minus A, this rho is 3/4. And therefore the spectrum has the form x squared. I have forgotten to put here x squared. So they put x squared. So for V minus A, the spectrum is x squared, 3 minus 2x. So that describes such a form, and the maximum is at x equals 1. Okay? Probably we'll have an exercise to check these things. Before computing decay rate or lifetime of muon, let me introduce precise the notion of decay rate. Some questions to this part?
I remember that in the various beta decays we have that GEF could be parameterized with a complete constant over the mass of the W boson. In this case, it would be a certain analog, right?
Yes, we will see this later. So for time being, that was actually already idea of Fermi, that G Fermi is actually is a constant square of the mass squared. And of course, in this case, people already start to think that maybe we have the same in the case of muon decay.
Does rho is equal to 3/4 corresponds to V minus A structure?
So this is corresponds to V minus A. So what is decay rate in general first? Decay rate is the probability of the decay in the unit of time. Suppose we have n particles. Then the change of the number of particles with time due to decay, dn over dt, will be given by minus gamma, and this is what we denote by gamma, multiplied by n. So gamma is probability of decay in the unit of time. And since we have n particles, then that will give us the number of particles decaying during delta t. So the equation is simply integrated, and we will have exponential law for number of particles observed, where n0 is the number of particles in the moment of time t. So it's just exponent. Now we introduce also lifetime of particle, which is inverse of decay rate. Tau is 1 over gamma. Now decay rate has dimension 1 over time or dimension of mass. Right, that's the dimension. Now let us derive expression for decay rate of muon. Gamma mu. So we will use again here dimensional arguments. And the important physical condition is that the mass of the muon is much bigger than the mass of electron. Remember, this is 1 over 10 of proton mass. And of course, it's much bigger than the mass of neutrino. Here it is non-zero. Now, since dimension of gamma is the mass, we can take into account this. And also we can write immediately that the gamma should be proportional to G mu square, right? Because G mu enters Hamiltonian, and therefore the amplitude will be proportional to G mu, and probability will be proportional to G mu square. Now, since this has dimension mass, this one has dimension 1 over the mass to the 4, then what is staying here should be function of these parameters, right? So something which depends on energy, and this should have the dimension mass to the 5th power. So, because of this inequality, the mass of electron and mass of neutrino can be neglected in the first approximation. By the way, this is not always correct. We will see decay of pi, for which these small parameters have become important also. So in many cases it works, but not in all the cases. And therefore we come to the conclusion that the gamma should be proportional to G mu square multiplied by the mass of the muon to the 5th power.
Even the mass of the electron can be neglected, but what about the energy of neutrino? But what about the energy of neutrino? Can that be neglected?
Well, this is total cross-section, total decay rate.
Okay.
So, which means that we integrate over final particles, energies and momenta. So then, the only what is available for you is this mass of the muon and these masses. And so that's what happens. You need to put here the mass in the 5th power, and that should be mass of the muon, with some corrections which of course depend on, let's say, 1 plus some ratio of mass of the electron of the mass of the muon, which we can neglect in the first approximation.
So you're saying that we're not looking at a reaction that suppose that there is a muon and it decays with a particular energy of neutrino. We're just saying that it decays. So you mean that you integrate over all the energies?
I'm integrating that. This is total decay rate. Because that's what determines lifetime of muon. You need to make integration over kinematical variables. Now, exact expression for gamma is G mu, at least in the lowest approximation, square, because then mass of the muon to the 5th power over 192 pi cubed. So of course this is big numeric parameter here, but you see one can even predict what is the power of of this pi, which should appear. And so this numeric parameter mostly is related to integration over momenta and energy of final particles. Let me remind you, and maybe some of you did these computations, then when we do integration over final particles, and here we have three particles in final state, right? Two neutrinos and electron, we have the triple integral in general, and it will be d pi vector over 2 pi q. So, and it will be the product I from 1 to 3, right? We have three integrals. But of course you have delta functions which take into account energy momentum conservation. And since you do integration over angular variables, it gives you some 2 pi or 4 pi. And in this way you can actually easily compute what should be the power of pi. I don't want to do this. If you want, you can check. So, that is kind of very expected appearance of this pi cube in this case. And here numeric coefficient, it should be at least 8 because we have 2 pi into cube. In fact, it is even bigger. So even this numeric coefficient can be, to a large extent, predicted without any computations. Okay?
But we know that when we do this computation, we have to impose energy momentum conservation at the direction of each current. So every energy momentum conservation.
No, I think if it's point-like interaction, you just apply this energy momentum conservation for whole the system.
You are taking it to be a point-like.
So it's we are point-like still, and this is a very good approximation as I mentioned already, and we will again confirm this. So that's point-like character at low energies, and energies are still relatively low. That works well. Now, what is important is this power, fifth power. And this is typical dependence, gamma to q to the fifth power, but this is energy release. For the processes when you have three particles in final state, and there's nothing special, some specific special cases exist. But in most of the cases, if you have three-body decay, then dependence on the energy release, and here energy release is mass of the muon, is the energy release to the fifth power. Just remember, it's useful because we will have many decays. But if it's three-body decay in with three particles in final state, the dependence should be as q to the fifth power.
Is it also true for beta decay?
It's also true, and if you, yeah,
okay,
absolutely. So, now lifetime was measured. A lifetime of muon is 2 to the minus 6 seconds. This is observation. And from here we can infer what is this G mu, right? Because total decay rate is just proportional to this G mu coupling. So in this way we can measure what is this G mu. And surprisingly, what we get is that this G mu is approximately equal to G Fermi. So everything is simple, right? Here. But you see how many important consequences follow from these simple things. One is the following. Muon has properties similar to properties of electron. Right? It's like a heavy electron. So it has spin 1/2. It has charge 1. It has no strong interactions. That was clear. So it looks like we have the second electron. Then the question is why nature created second electron. Why we can survive without probably muon. So our life would be quite the same, right? So we are made of atoms, and so you see the atoms, you have electrons, protons, and neutrons. You do not need muons, right, to build up all this what is surrounding us. This is still unsolved problem. So why we have particles with the same properties, this repetition of particles? This is the first kind of a sign of this what we call flavor problem, which we're still struggling to solve. So we have muon, which has 200 times bigger mass, and we don't know why it is 200 times bigger than the mass of the electron. Why we have this hierarchy of masses? And then we will discuss also discovery of tau lepton, which is again something like this electron and muon, but heavier. So this is open question still. So why we have this repetition of particles, but with bigger masses?
Now, I have a question which is a little related to this thing. We can predict the magnetic moment of electron to a great precision. Mm-hmm. But what happens? Why are we not able to do that for the muon particle?
Well, we can do this. There is kind of anomalous magnetic moment, which is probably so. In the first approximation, you know what is magnetic moment.
But do we know that particular magnetic moment to 12 decimal places, like do we know for electrons?
No, because we have still some problem, which actually, so we can make computation in the standard model, but then what has been observed, there's some deviation from what has been predicted, although it's not so easy to predict, because here you need to take into account also even some hadronic corrections, or corrections due to strongly interacting particles. So let me just say that soon we will have some experiments which will again measure this so-called anomalous magnetic moment, and then maybe we will resolve this problem.
Can we say that the difference between the muon and electron is not just in the mass? Because if it was just the mass...
Yes, this is just because of mass, because you have some corrections to the radiative corrections to the magnetic moment, well, at least as we understand it now. And so there are loops, because if you want to have many decimals, you need to take into account high order corrections, and then you need to take into account corrections when you have quarks running in your loops, and here you have uncertainty. Maybe this is some new physics. Okay, so now the question why people are so interested. There is this deviation, and of course people think that maybe there is some new physics. If so, that maybe electron and muon have different properties with respect to this new physics. Yeah. That we don't know yet. But you are kind of jumping too far.
It could also be because of the experimental difficulty of having that the muon will decay very soon. Maybe that's also something to...
Well, this is not soon. Actually, can you imagine that that at particle scale, muon is very long living particle. So shortly living particles has 10 to the minus 23 seconds, 10 to the minus 24. And so people are discussing even to create muon accelerators. So it lives so long, but also you have this Lorentz boost if you accelerate your muon to higher energies. But it lives enough to create these muons, to cool them, to accelerate, and then to make experiments. This is huge time.
Okay, so the idea is that...
It's like you compare your lifetime with the age of the universe, creation of stars and something like that.
Yeah.
Even bigger difference here.
I see, so the problem in the anomalous magnetic moment for the muon would be those radiative corrections. It's not because of the...
This is what people are blaming. So again, the observations.
Yeah.
Still, it can be some experimental feature, as usual. So we don't know exactly if it is confirmed, and and there are specific measurements which actually can improve our understanding of radiative corrections. Mm-hmm. So if this is established, this discrepancy, this means there's some new physics beyond the standard model. So that is a conclusion. And there's a number of models, many models, with some new heavy particles, probably this is approach to flavor physics. Then you probably have some understanding why there is something else apart from mass which distinguishes muon and electron. This is within 1-2 years. We may probably clarify what's going on. Okay. So again, discovery of muon created so-called mu-E problem. What we have discussed. That actually indicates towards some universality. So this is the first hint that we deal with universality. Which means that different processes have the Hamiltonians behind, which have the same structure, the product of currents and the same coupling. So without this, we would not construct standard model. That would be something else. So this is one of the milestones in the standard model is universality. And here you see the first hint of universality quality of couplings, and the same form of the Hamiltonian, which we use for beta decay and here for muon decay. Okay. So now next discovery is discovery of pion. And properties. So the history of this discovery is the following.
Just a question before moving on. The G mu was close to G Fermi. Is that something generic for weak interactions in low energies?
This is what we will see.
So even, let's say, if you had G of tau, it would be also close to G Fermi?
Yes.
Okay, so
this is experimental fact. You see, for time being, I'm not speculating. So that was the result of observations.
I see. But the underlying theory will be compliant with weak interactions, I see.
Yeah, this is the feature, universality of weak interactions, yeah.
Okay. That's fine.
So we will continue with this universality later. So what is the history? And history starts from Yukawa. And Yukawa has constructed the theory, the first theory of strong interactions. So it was clear, and a structure of nuclei has been developed. So they are composed with protons and neutrons, and it should be strong force which keeps these protons and neutrons inside the nuclei. Especially we have, say, protons or several protons inside the nuclei. And of course there is a repulsion, and so you need to introduce even much stronger forces which keep all these guys inside the nuclei. And what Yukawa did, he proposed that there are some forces due to mediators, due to some new particles, which are exchanged between protons and neutrons. So let me put nucleons. We use for protons and neutrons this notion of nucleons. Don't confuse with nuclei. So he introduced the particle which leads to this exchange. Actually here it could be prime and it could be prime prime. And so P prime. So it can be proton, neutron, and then can be change of the charge. So proton can go to neutron. And then these particles have both positive and negative charge. So these particles should be massive, because you want to explain short-range forces. Nuclei have some small size, and you want to introduce something which actually gives you these compact systems, and therefore the mass of the pion should be like 1 over the radius of nuclei, typical size. And so one can find that that corresponds to mass of the 100 MeVs. 100 MeV. So the mass should be 100 MeVs. The size of the nuclei is inverse of this 100 MeVs. Okay? And just using this exchange, this diagram, one can find what are the forces and what is the potential for this interaction. And that is proportional to 1 over r, and then exponent into minus the mass of the pion and r. So that, and then derivative gives you the force. And coupling, and here should be coupling should be very big. So coupling should be bigger than 1 to explain that you keep your hadrons, your protons and neutrons inside the hadrons. Okay, so diagrammatically, the plot is like this. At very small radii, it's like a Coulomb force, but then there's this exponential cutoff at the radius as inverse of the mass of the proton, mass of the pion, this particle, and this is potential. And this is dependence of the potential on the radius. Now, when muon has been discovered, the first idea was that probably muon is this Yukawa particle. But then the lifetime of muon and interactions of muon do not match the properties which are expected for pion. And later pion decay has been measured, and it was established that this is Yukawa particle. Now, this is again extremely important particle because it led eventually to classification of hadrons and to quark picture.
So say that because this pion is exchanged between the nucleons, and the nuclear force doesn't distinguish a lot between protons and neutrons. So we can say that because it is.
Sorry, the force is what?
It doesn't matter a lot that you are exchanging between. That's
right. So it's the same for proton, and we will discuss this isotopical symmetry later.
So we can say that it is also exchanged between neutrons and neutrons. So pion should be pion should have a species which is neutral.
Yes.
So muons cannot be pions because they are not neutral.
Right. So when again, so the muon has been, who knows, maybe there is a neutral muon.
Okay.
Yeah? So, or heavy neutrino, we are still struggling actually to discover this. So, what has also been later understood that these couplings are the same. So actually, we can introduce the same couplings for protons and neutrons, and this is the feature of symmetry behind these equalities of interaction. Okay. Actually, let me add something more. Again, pion is extremely important particle, and you will see that chiral perturbation theory has been introduced just on the basis of pions. It's interesting that it's just a single particle, but it leads to so big developments after all. So that you will see. Then pion is important from a practical point of view because pions are actually the main source of neutrinos. In many experiments, we have pion decays as the source of neutrinos. Now let me discuss discovery. So pion has been discovered by Bristol group in UK. In 1947, it's already after the war, and the authors of discovery were Lattice, Occhialini. And power. So this is Italian, this is Brazilian. Guys worked in UK. The source of bias was again cosmic ray, but the detector was different from what we have discussed before, and as the detector people used photoemulsions. So let me say a few words about this technique using photoemulsions. And even these days people are using more sophisticated, but still this type of the technique. And this is another way to visualize the tracks of the particles. So this technique uses again something which is triggered by ionization. So charged particle is moving in this emulsion, produce ionization, and then there are ways to actually to visualize this track. In this experiment, what people used, they used HEP, which is silver bromide. So this material is transparent for light. And then the detection actually was in 3 steps. The first is ionization. Ionization of these molecules. So you have track of the particle and ions on the track. Second step is development of emulsion. This is chemical procedure, which actually leads of conversion of these ionized molecules, ions, to separate molecules of silver. So this big molecule of silver bromide then splits, and we have production of molecules of silver. And the third step is that what happens is that these molecules or atoms of silver start to create grains, so they group with each other. So this is kind of chemistry. So potential energy decreases when these atoms are not separated but form the groups. So formation of grains. Of silver atoms. These grains already become opaque for the light, and therefore you can see these grains, which are quite big. You can see these grains on the background of transparent silver bromide.
In the first step, the charged particle goes through silver bromide, or is it something?
Yeah.
Silver bromide.
Yeah.
And it is in the liquid form.
So this is not liquid. So that's this is like this is emulsion, what we call. This is some substance which can be solid actually.
So can it be a solution of silver bromide?
Well, probably, but this is what has not been used. It's like a film. It's like a film, like photographic film.
So in the second step, the ions that form, that they become silver molecules.
So that atoms, and sometimes they start to group, and so this will be silver with say 2 atoms, and then they group into big grains.
So in the first step, the ions that were formed were of the ions of silver.
Well, this is ions of this. No, it's ions of this molecule. So some electrons are thrown out, and then chemical procedure, which I don't know how it works. So this is chemistry, no? So that leads to split of these ionized molecules onto bromide and then silver.
It may happen that the electron goes from the bromine and the hydrogen ions in the water can suck the bromine and the silver is separated.
Well, you have, again, so always you can have with certain probability different processes as usual. So that what is one of the branch of what's going on. Usually it's very complicated, you may have different possibilities, but this is one which actually is used to see these tracks.
But the end result is that the silver molecules will form and will form grains.
And they will form grains, yeah. And these grains can be seen. So, you see, this is another way to visualize the tracks. And of course, we see something which is big, relatively big. And it comes from these initially elementary processes of ionization.
Can this whole procedure of the formation of silver grains happen without an ionization procedure? That there was no particles.
Well, if there is something which ionized, then that can proceed. But if it is not ionized, maybe I don't think so.
So the grains will form only if a particle comes and ionizes.
When something ionizes.
Okay.
Now, what are observations? So they saw some tracks of the following form. And I will show you the slides actually with this. And there are many tracks of this type they saw. This is already kind of classical picture. So they saw the tracks with 3 sections. What are the properties of these tracks? And let me denote them as 1, the first track, the second one, the third, and we have 2 vertices. Here is A, and here is B. So the properties are the following. The track 1 and track 2, they become thicker. So that's like this. Which looks like you have some particle which loses energy on to ionization, and then it looks like it stops and then decays, right? So the first is track 1 and 2 becomes thicker. The track 3 oppositely becomes thinner, which looks like you have something which loses energy onto radiation, and so that track has been identified with the track of electron. It looks like this is electron track. But the key feature is that the intermediate track was actually the same, practically the same for all the events. So track 2 has the same length for all the events observed.
Are these tracks forming when we place a detector in the magnetic field?
They didn't use magnetic field. So there were these emulsions without magnetic field. So, interpretation. So how to explain this?
As I said, it might be because of that decay.
Because of?
Decay?
Yeah, clearly there's some decays here, and probably emission of some neutrinos and visible particles, because you have energy momentum non-conservation for visible particles from these tracks.
So the first particle should be a heavy one because it is non-relativistic, that's why it is losing energy by ionization.
Yes, yes, so then
The second particle should be
and you see what actually, how people analyze data. So they make some assumptions. So let's try to have this interpretation and then check everything, and maybe you want to have additional experiment to check if our interpretation is correct or not. And one can, in some cases, many different interpretations are proposed to explain the observations, and then detailed analysis and additional measurements allow to select correct interpretation. So let's see how it works here. What was assumed, this is assumption, and then we will check if it works or not. So what was assumed? That track 1 is due to some new particle. And let me call it immediately pi. Now the question is how to explain the same sizes of the second track. Because you see, if you have some particle, and it seems that this particle is decaying, so it decays in the vertex in the point A, and it produces second particle, right? Then imagine that that this particle is also decaying, because it looks like in the point B this particle decays, right? So we have lifetime of the particle, but lifetime means that this is average lifetime, and then quantum nature appears so that in one event the particle lives, say, 1 second, and another one 5 seconds, and the third event 0.5 second. So this of course fluctuates, right? It depends. This is quantum mechanics. It's quantum. So how you can get in the same lengths of the tracks? So it looks like this particle is living. There's no quantum nature, so it lives precisely a certain amount of time. So you understand the problem, right? So if you have decay, then in various decays you have distribution, right, on the lifetime. So you have this exponent. So you have a possibility of decay in a big range. So one would expect from this point that so in one decay the track is like this, and another one like this, and the third one like this.
If the decay at point A is a two-body decay, then there will not be any distribution, there will be a fixed energy.
But even for fixed energy, yes, so this is not sufficient. This is necessary, but it is not sufficient, because even if you have decay at rest, and so that you're right, so this is what has been assumed. So decays in point at rest. And this is two-body decay. So that in all the processes, the energy of this particle is the same, right? Because you have this ion, which loses the energy, stops, and decays. And it has decay into two particles. And one is, again, neutrino is blamed for this. And the interpretation was that pion decays into muon plus neutrino. Since pion decays at rest, muons have the same energy in all the decays. Again, so this is some assumption, hypothesis, and so eventually one needs to check again and again if it works or not. Now, why then muon has the same tracks? The same lengths of the tracks. How to explain this? This can be explained in the following way. So the tracks become thicker, which means that muon loses the energy on ionization, stops, and then decays. Now, let us assume that lifetime of muon is bigger or much bigger than the time of energy loss. So, which means that it first stops and then decays. So muon stops and then decays. Otherwise, we would have different sizes of the tracks. Okay? Now, then the length of this track is just determined by the time or the distance of energy loss. The energy loss is not just a single process. It's multiple process because particle is moving and ionizing medium, right? When you have many collisions, then you have essentially classical property. If it is many, so you can have some fluctuations in individual collisions, but when you have many collisions, then everything is average, so fluctuations are averaged. And therefore, the time or the distance required to lose the energy completely is the same in all these tracks and all these events. Okay? And then here muon decays with emission of 2 neutrinos. So this is interpretation of these events. And then people analyzed many of these type of events, and so this interpretation has been confirmed.
With this hypothesis, what you can do is to set a maximum length, but it can also decay while it's moving.
Well, again, if you have this inequality, then the number of events, it can still have some chance to decay.
But the chance is very
But
small.
it's small, so of course you may have the possibility that, say muon decays here before it's losing the energy. That can happen, but again, the number of events expected is much smaller. So this is inequality of lifetime.
You can say that the distance between A and B is the same for every track.
Yeah.
But the time is not the same.
Well, it's why? Why?
Because it can happen that muon loses all the energy and then decays immediately. And it can also happen that muon loses all the energy and it stays for a while.
Well, no, because the loss of the energy is in each of these collisions is very small.
Okay, so
Again,
immediately after.
the probability that it will, there is still some probability that muon immediately loses the energy, so it can be even absorbed, something like this. So now quantum mechanics enters, right? So this is kind of very classical description. However, for this type of the things, you need really to keep in mind quantum mechanics. Yes, muon has a possibility to decay very quickly or to lose the energy. However, say probability of these events is 10 to the minus 5 or 10 to the minus 7.
No,
Which means
I'm not saying that. I'm saying that the energy in a single collision is very small. And suppose that after a finite amount of distance, muon has lost all of its energy. But it doesn't decay immediately. It can decay after a certain amount.
oh yeah, so in this sense, yeah, okay, yeah, sure,
So that's
absolutely,
why
I agree. Oh, so that's true.
So the time should not be the same.
Sure, time is approximately the same. but it can still stay in weight before decay. True. Okay. So the size, the distance is the same.
It could also happen that instead of decaying into muon, it could decay into electron.
That we will discuss.
But it will be a different probability, right? It should be smaller than decaying into muon.
Yes.
Okay.
Yes. This we will. That we will discuss now. Okay. Clear? So you see, although it looks like everything is simple, right? So still you need to have some kind of intellectual work, you know, to give this interpretation of the event. So it's not like it's very simple and immediate. So now let us develop the theory of pion decay.
I have a question.
Yeah.
Could this discovery be made in a Wilson chamber?
No, it's emulsion chamber, emulsions. So they have these films with emulsions, and so they then develop emulsions like photographic emulsions. Okay.
He just saying that.
So these are the tracks which are formed by these clusters of grains of silver.
No, he is asking that can we do it in a Wilson chamber too?
Yes, sure, sure. But that's how it was discovered. Okay, that's pion theory. So here we deal with the process when pion is transformed to muon and neutrino. So clearly this is weak interaction process. Once neutrino appears, that immediately testifies that we deal here with weak interactions. Then we have here lepton pairs, and again using analogy we can guess that the interaction here again occurs due to interactions of currents. And what we can write, the Hamiltonian responsible for this process is some G again. Let me put here pion over square root of 2. And then we can write this leptonic current. And we know how it looks like, so we can guess it's the same as in the case of muon decay. It is composed of muon, then gamma mu, 1 minus gamma phi, and then neutrino. Alright, so we know what is this. This is our leptonic current. But now we can guess that maybe some hadronic current is also involved, which is responsible for disappearance of pion. Now this is very important trick, and you need to kind of understand this. Let me put this plus Hermitian conjugate, and to say that this is hadronic current. Although we don't know explicitly what is the form of this current, the only what we know that it should be some mu here to have invariance, Lorentz invariance. We need to have some operator here which has this index mu. Once we decided that a lepton pair is described by this leptonic current, and to have Lorentz invariance, we need to multiply this by something which brings this index mu, right? And which is responsible for disappearance of pion. And let us call this also current. Again, using analogy, is what we learned already from other decades.
Okay, can we, using this form of Hamiltonian, can we just speculate that, if pion was made up of 2 fermions, then we will know the form of the current. So
right. So you're moving things. Eventually, when we go to quark picture, that will be happen. What will happen actually, because pion is composed of quark and antiquark. And then at the quark level, that analogy will be really complete. So it will be again the current when we have 2 fermions. Here we have no fermions. Remember previous processes we discussed were 4 fermion processes. 4 fermions were involved in the decays. Now here, as you see, this is boson. Oh, by the way, I haven't mentioned, so the pi to have decay into muon and to neutrino, the guy should have integer spin, and the simplest possibility is spin 0. And there were also studies and spin has been checked. So it has spin 0. You see the muon and neutrino have spin 1/2, so that should be integer. Okay? So, using this we can actually proceed quite far. Even not knowing the kind of the precise form. Actually, whole the current algebra has been developed without even specifying what is the form of these currents, but just using symmetries and Lorentz covariance, you can actually get a lot of results. So the amplitude of pi decay can be written as, so this is matrix element between mu and a neutrino, so mu and neutrino, then Hamiltonian, and pi. And knowing this factorized picture, we can rewrite this as g pi, over square root of 2. And then we can split this into 2 matrix elements. One is responsible for disappearance of pi. This is hadronic part, so it's H mu. And leptonic pair, mu. Let me put mu if you want. So then we will discuss that if this is different or not from electron neutrino. And here we have leptonic current. It's L mu, and here is 0. So, in initial state we have pi, and we need this current to transform it to vacuum, to nothing, right? So there is no hadron in final state. Inversely, in initial state we have no leptons, and we need this current to create this pair, muon and muon neutrino, in the same way as leptonic current created pair of electron and electron neutrino in beta decays. Again, we're heavily using analogy. The formalism is developed by analogy. And till it works fine, so if it doesn't work, then we need to start to think. But this is how the history was.
You have inserted a complete basis.
Sorry?
You have inserted vacuum in the second step, so you have.
No, I don't need to do this. So that's actually my initial state is 0 pines in final state and 0 leptonic pair in initial state. Maybe I should not delete this. Now, what is this hadronic matrix element? 0 hadronic mu pi. So eventually, as I already discussed, all these computations lead to some expressions which are functions of kinematic variables. So which means that eventually this matrix element should be some function of kinematical variables. And there is no big choice, right? Because we have only one particle pi, and the only what we can write to have a covariance. So the only what we can write here is the momentum of pi. There is nothing else, right? So this matrix element must be proportional to momentum of pi. And then we need to multiply by some coupling. So let us multiply by coupling f pi. And using dimensional arguments, probably we'll have some exercise for this. You can find out that dimension of this f pi should be dimension of mass. And numerically, what is interesting, that this f pi is approximately the mass of pi, and this is 100. So this f pi is 130 MeVs. Approximately mass of the prime. And this is measured. Okay. So this coupling, decay coupling of prime, plays crucial role actually in this chiral perturbation theory. And so that's very important parameter. So let us proceed with our computations, and I will finish soon. Energy momentum conservation tells us that the pion momentum should be equal to neutrino plus muon momentum for this vertex. So now we will use this expression for hadronic current element, and for this everything is known. We know the structure of this current, we know what are these wave functions of muon and muon neutrino, and so we can write what is the amplitude immediately.
When you, we know that the current is a Lorentz vector, right?
Yeah.
So would it be possible that you don't use mu because it confuses with the mu on the...
Oh yeah, so we can use a nu alpha if you want, sure. So let me, I don't think that you will confuse much, but anyway, we can use some other index. Yeah, so if you want, you can use here alpha. I don't want to use mu. So alpha and alpha here. Yeah, so here we can use alpha. And alpha is 0, 1, 2, 3. Right? That's, okay. So now we will write our amplitude using this expression. You have it already written somewhere. So I can write it as A equals G pi square root of 2 F pi. And then now I'm writing momentum of pion in this form. That will be P neutrino alpha plus P muon alpha. And so the rest is U muon. This is for spinor. This is what is left after we do computations. You will do this at once. But when you do this kind of computations of matrix elements, current is known, and the states are known, so you can use asymptotic states, which are plane waves of muon and neutrino for them. And so here is for spinor already. Then gamma alpha, 1 minus gamma 5. And here is spinor, which corresponds to neutrino.
And these spinors depend upon the momentum of the
Yeah, yeah. So now we can rewrite this as G pi. Sorry, I might take probably 5 minutes, no more. F pi. And then what I will do, you see I have two terms. One is P alpha, another is for neutrino, and another P alpha for muon. And I can write these two terms in the following form. U mu, then P muon alpha, right? And you put dagger when I multiply by gamma. What do you use, or just cross? So
slash.
Cross, okay, slash. Now let's use slash. Right, so what I'm doing, I'm combining with this gamma alpha. So I take this P alpha mu, multiply by this, I get this one. And then there will be 1 minus gamma 5, which is left. And neutrino spinor plus, I use for neutrino, and I can write this as U mu. Then 1 plus gamma 5, because I want to put this, transpose this, and to attach this to neutrino spinor. So let me put here, and I will explain again. P alpha should be no alpha, right? So it should be here neutrino, and this is U nu. So what I did in the second term is the following. I attach this neutrino momentum to gamma alpha and then transpose with 1 minus gamma 5, it becomes 1 plus gamma 5. Right? Now what I'm using Dirac equation, and then this just equals u mu multiplied by the mass of the muon, right? And here it will be m neutrino multiplied by spinor of neutrino. And I will neglect this term a second because of smallness of neutrino mass. So the main is this one. Let me write it again. So the amplitude equals g pi square root of 2 mass of the muon f pi, and then I will have u mu 1 minus gamma 5 u mu, and these are spinors. Okay. So now I can immediately compute what is gamma decay rate, which is moduli square, which is proportional to moduli square of A. And that will be proportional to g pi square, mass of the muon square, f pi square, and then I need to add something which is of the dimension mass.
That is the mass of the muon.
And what I should add here, clearly, for particle to decay, particle should have a mass. And therefore, X should contain the mass of the pion. So it should be the function of pion, and neglecting mass of neutrino and the mass of muon. Right? And of course, if the mass of the muon and mass of the pion are equal, then there is no decay. So decay rate should be 0 in the limit when mass of the pion equals to mass of the muon. And therefore, the factor x, which appears here, is just given by the mass of the pion, then 1 minus mass of the muon square, mass of the pion square, and everything square. So it should be some factor which is 0 when mass of the muon equals to mass of the pion. It's clear, so right? And then it should have a dimension mass. So the only what we can write is the mass of the pion and this factor. And of course, if the mass of the muon is 0, then it should be just mass of the pion.
Instead of mass of pion.
Oh, sorry, that's mass of the muon. Yeah, that's important. This is mass of the muon. Sure. Thank you. This is mass of the muon. So now the question is, can I have decay into electron and electron neutrino? So what about, and this is the last point, what about the decay of pion into electron and neutrino? Does it decay? And is this channel exists or not?
It would be similar, but with, instead of mass of muon, it would be mass of electron, right? It would be something very similar.
Yeah. So, by the way, I probably should write also exact coefficients. So let me write first. I have forgotten to write this. That if I do exact computations. Again, so I'm very close actually to exact computations with this formula. You can rewrite it again. This will be 8 pi, and this is gamma equals. So up to this 8 pi, and actually I can predict this existence of pi with this 2 pi. So up to numerical coefficient, I'm getting this formula, and let me write it completely. So it will be mass of the pion, and then I'm okay with dimensions, and then it will be 1 over the mass of the muon square, mass of the pion squared. So this is final expression for gamma. And as you say correctly, for this mode, I need to substitute here mass of the muon by the mass of the electron. Also here, but the electron is much lighter, so I can't even neglect here things. So why it happens so?
But it is almost 4,000 times less.
Yes, so that's why actually pion decay is very pure source of muon neutrinos. This is extremely important for oscillation experiments, which we will discuss later. So again, remember, for this reason, pion is the source almost pure muon neutrino beam. So you create pions in your accelerators, and then they decay, and in this way you are producing the beam of muon neutrinos. Now, can you guess why, from physics point of view, I have here mass of the electron, which means that this mode is very strongly suppressed, counterintuitive, because here these two particles are very light. Remember that muon has the mass 105 MeVs, pion has 140 MeVs, not far from each other. Here the mass of the electron is much smaller. Why then this mode doesn't dominate? We have this formal derivation, so what is the physics? What is the physical meaning of all this?
I think it has to do with something with helicity in this conservation and decay, and the fact that you have only left-handed neutrinos.
So you will have an exercise. You are kind of on the right track, and the point is that you can get these factors from angular momentum conservation. And the point is that to satisfy angular momentum conservation for this V minus A theory, which we are discussing here, you need to make a flip of helicity. But again, after we will discuss parity violation, then you will have an exercise to use angular momentum conservation for the particle. And what you have pion. Take pion at rest and has zero spin. And then you have muon and say muon antineutrino, or electron and electron antineutrino. And then you need to know what are spin states of this. And then apply angular momentum conservation, and then you will get this factor. In one case you will have the mass of muon, and another mass of the electron. So since we are late today, so probably I will start to meet with you tomorrow. So what I'm asking, say, two of you come to my office and I'll just discuss for 5-10 minutes. Usually I'm asking questions of what you have studied in your university precisely. So what you are interested in, do you have an idea what you want to work on? Things like that, right? And so also asking about my course, if it is clear or not, should I move faster or not, provide more details or things like that. So then I will adjust more precisely to your level. Okay, so tomorrow I will also expect from you exercises, solutions, exercises.